All right, so okay, we are finally starting magnetic fields. Yeah. So we'll study magnetic fields. Okay. Again, we mentioned this before. Um, um, Charge at rest will produce electric fields. Okay. And a moving charge will produce both electric fields and now I'm going to give you the configuration of the magnetic field. But so if a charge is moving in this direction, what it does is it produces magnetic fields that are tangent to cylinders. Magnetic fields are denoted by B. Okay, so moving charge will produce both an electric field and magnetic field. Yeah. So over the next two chapters, this is what we'll study. We'll study the magnetic fields produced by moving charges. All right, all magnetic fields are produced by moving charges. All right, now here's another interesting fact. Okay, so again, charges at rest produce electric fields, charges and moving charges produce magnetic fields. Okay, now let's look at the situation the following way. All right, so here's a charge at rest in lab, and you're in lab there. What do you see? That this guy produces an electric field. Okay? Now here's your buddy, and here's your buddy, and he's driving by in a car. What does he see? That's right. So this guy, okay, to him, this electric field appears as both an electric field and a magnetic field. Okay, so he sees a magnetic field as well. Okay. All right. So that's a beautiful thing. Okay, again, what did we say? Moving charges produce these magnetic fields. Okay, so now let's talk about magnetic fields. So initially, we'll start off by just talking about magnets. Okay, so here's a magnet. I mean, these are all different kinds of magnets. Here's a magnet, and these magnets. So here's a magnet. These magnets produce these magnetic fields around them. So that's what we're going to study. Okay. What I said to you initially, that you'll learn over this chapter and next chapter. Okay. All right, so we said magnetic fields are produced by what? Moving charges. Where's the moving charge in here?
Is it inside the material itself?
Yeah, what is moving? Where's the charge moving?
The electrons are moving between the various poles.
No.
Bouncing around like a gas particle inside the material.
Yeah. Well, that random motion won't give rise to magnetic fields. Well, I mean, it'll give rise to magnetic fields, but which will cancel. Okay, so it's again, yes, so it's electrons within the atoms that are moving that are producing the magnetic fields. Okay, so in most materials, well, all electrons spin, and all electrons act like a magnet. Okay, they're charges in motion. Okay, and so in materials where the magnetic moments, their magnetism doesn't cancel, then you'll see it magnetism in bulk. Okay, so anyway, just remember that all magnetic fields are essentially results of moving charges. Okay. Okay.
But everything has a magnetic field, doesn't it?
What's that?
Everything has a magnetic field.
All right, so let's answer that question. Okay. Oops, I shouldn't have erased that. All right, so here's an atom. Here's a helium atom. Okay, so here's an electron going around in this orbit like that. Okay, that'll produce a magnetic field. And you'll see this. So if you hold your fingers, if you use your right hand and hold your fingers pointing in this direction, your thumb will point in the direction of the magnetic field. Okay. So if you have a current flowing like that, so if an electron travels, a proton travels in this direction, it'll produce a magnetic field like that. Okay. A ring of current like that will produce a magnetic field like that of a magnet. Okay, so the fields will look like this. Okay. So a current flowing like so will produce magnetic field lines like this, which is the magnetic field exactly like that of a bar magnet. So what we are saying is a current carrying ring, a ring of current, behaves like a bar magnet. Okay. All right. Let me show you the Earth's magnetic field. Yeah. So there is the North Pole, there is the South Pole. This is the geographic North Pole and the South Pole. And the Earth's magnetic field there is the Earth's magnetic field. Okay, let me show you this diagram again. Okay, a ring of current like this produces this magnetic field. You see this magnetic field pattern? And here's the Earth's magnetic field. What do you conclude from that? How are magnetic fields produced? Moving charges.
Is there a ring of current parallel to the equator?
So there is a current inside the Earth that's producing that magnetic field. Very good. What carries currents? Liquid metals. What's that?
What was the question?
What carries currents? So liquid metals. So if a planet has a magnetic field, that means there is a liquid metal core where there is a current flowing. All right, so keep that in mind. We'll talk about that later in the chapter. Okay? All right, so again, these are the Maxwell's equations that we keep talking about. These are the causes, these are the effects. This is a charge density. Charges produce electric fields. We'll talk about that later. Changing time-varying magnetic fields will produce electric fields. Okay. Moving charges, that's current density. Moving charges produce magnetic fields. So we'll talk about this half of the equation in this chapter and the next chapter. So just half of this equation, and we'll dedicate 2 chapters to it. What does this part of the equation tell you? Time-varying electric fields act like currents as well. Okay? And they can also produce magnetic fields. Okay? We'll talk about this maybe 4 chapters from now. Okay? So moving charges produce magnetic fields. Okay? And the form of this equation tells you the configuration. So for instance, if a current is flowing like that, it produces magnetic fields that are concentric circles like this. Okay? So that's what this equation is telling you, one of the things it's telling you. Okay? So again, you stick your thumb out in the direction of the current, and your fingers point in the direction of the magnetic field. So magnetic fields are tangent to this thing. Okay? And also, the further out you are from the current, the weaker the magnetic field. Okay. Did you guys understand all of that? What produces magnetic fields? What produces magnetic fields? Moving charges. Okay. And so here's a beautiful symmetric thing. Okay. Stationary charges produce electric fields. Moving charges produce both magnetic fields and electric fields. Okay. And once you produce the field, whatever produces the field, that's what detects the field. Okay. See, to detect an electric field, you need a charge. So that's the force felt by the charge. And to detect a magnetic field, you need a moving charge. Okay. So moving charges produce magnetic field, and to detect a magnetic field, you need a moving charge. Okay, so there's a beautiful symmetry there. Okay, so these are the Maxwell's equations in differential equation forms, the same equations in integral form. Okay. All right, so I gave you a 30,000 foot view of it. Now we'll get into little details, some of the nitty-gritty. Okay. All right, so these are various shapes of magnets. All magnets come in with two poles. Okay, so you can go to a store and buy a positive charge and a negative charge, but you can't go to a store and buy just a north pole and a south pole. Okay, they always are sold in pairs. Okay, so there are some theories, these are called monopoles. Some theories posit the existence of monopoles, but right now, well, we haven't discovered them. So right now, all magnetic fields are produced by moving charges, currents. Okay. All right, so these moving currents, they have you can explain a lot of things by assuming a north and a south pole. Okay. Like poles repel each other. So if you take two magnets, like poles repel each other. And unlike poles, a north pole is attracted by a south pole. Okay. So that's the behavior. Like poles repel each other and unlike poles attract. The force between two poles varies inversely as the square of the distance. What does that statement mean?
It decreases exponentially.
No, it decreases, is proportional to 1 over r squared. Okay, you double the distance between the poles, the force decreases by a factor of 4. Okay, so it's an inverse square law, just like gravitation, just like the force between charges and so on. Okay. So here's a material that is magnetic. Okay, and like I said, ultimately electrons spin, and those spinning electrons act like magnets. Okay, so in a bulk material, if you see magnetism, it's the effect of the sum of all those magnetisms. Okay, if something is not magnetic, every electron is a magnet. So if a material is not magnetic, what does it mean? Does it not have an electron, or does it not have electrons, or all the magnetism of the electrons are canceling each other? Okay, that's what that means. So for every electron going around like that, you have an electron moving in the opposite direction. So the orbital magnetic moments cancel. For every electron spinning, you have an opposite spin. Okay. So if a material is not magnetic, then all the magnetism of all the electrons are canceling each other. Okay. Again, now that's a microscopic view, but here's a macroscopic thing. All right, so you go and buy a magnet in a store, break it into two. You don't destroy its magnetism, you get two magnets. You break that into two, you get two more magnets. How far can you go?
All the way down.
What is all the way down? I'm sorry?
Pieces of the magnet left.
Hmm?
Until you're down to one magnetic atom.
Until you're down to an atom. Okay? And that is magnetic. All right? So you never destroy magnetism. Well, what you can do is if you want to destroy the magnet, so this magnet is made of billions of microscopic magnets. And if you want to so if this piece is magnetic, that means all those microscopic magnets are aligned. If you want to destroy the magnetism, what you do is you randomly align all of them. Okay? And you'll see that next chapter. And as an engineer, you will need to do that. You'll use soft magnets where you're aligning and randomizing those alignments all the time. Okay. So what are magnetic monopoles? Again, just a north pole by itself is a monopole, a south pole by itself is a monopole. We haven't seen them. Some theories postulate them. Charges you've seen. Okay. You guys understanding this? Okay. All right, so here's a magnetic material. Here's a magnet. What does the magnet do? It creates a magnetic field all around it. We've already drawn the lines for you. How do we detect this magnetic fields? Well, I told you need a moving charge, but so you get other little magnets which have moving charges in them. Okay, and here's a compass needle, and the compass needle lines up with the magnetic field. It's tangent to the magnetic field line. So at this point, the field line is pointing like this, and the north pole points towards the south pole of this magnet. Okay. So again, okay. So this is how the field lines look like. Magnetic field lines. They start on the north pole and they end at the south pole. And field lines do not cross each other. Okay. Do these lines look familiar? Have you done anything like this? Yeah, so the electric field lines of a dipole look exactly like that. Okay, that's the lab you guys did. Yeah. So these are the magnetic field lines, and magnetic field lines exist around magnetic materials. Again, like we said, moving charged particles and time-varying electric fields are sources of magnetic fields. Okay, and that's contained in this equation. Moving charges are producing magnetic fields. Time-varying electric fields also produce magnetic fields. Okay, so that's that statement. They're denoted by B. So magnetic fields at a point. So magnetic fields at a point can be defined by defined in terms of the force they exert on a moving charge. How strong is the magnetic field here, and in what direction is it pointing? You can figure that out by using a moving charge. Okay, so that's how you detect magnetic fields. Okay, so here's the force, magnetic force on a moving charged particle. So for instance, if the particle was at rest, if V was 0, the force on that particle would be 0. The magnetic force would be 0. Okay? And you couldn't detect it. Okay, so you need the charge to be moving. If the particle was uncharged, there would be no force. You can't detect the magnetic field. So you need the particle to be charged and moving to detect this magnetic field. All right, so the magnetic force is a cross product of these two. It's V cross B. Okay, so let's say, so here is the particle is moving in this direction. Here's a positive charge moving in this direction, and the magnetic field is like that. So V cross B, Now you'll need to do this, so in a lot of these problems, you'll have three-dimensional things. So V cross B, here's the best way to remember it. So the direction of a vector A cross B, how do you figure out the direction of a vector A cross B? Here is A, B. Okay. You turn from A to B. If you turn from A to B, if you turn a screw from A to B, which way would the screw move? So the screw would move forward in this direction, okay? And that's the direction of A cross B.
So one like shooting out.
It's perpendicular to the plane containing A and B.
Yeah.
Okay. So imagine a screw again. I'm recording, and so I'm trying to draw everything, but if you turn a screw from here to there, in this direction, the screw would move up. Okay? And that's the direction of the cross product. Okay? So for instance, if V was like this and B was like that, so if you turn a screw from V to B, it would move in this direction, and the force would be in that direction. Okay? So what we are saying is, if you had a magnetic field like this, you throw a positive charged particle in that direction, the force on the particle will be like that. So now here's the deal. Okay, so a moving charged particle in the presence of a magnetic field feels a force perpendicular to its direction of motion. When you apply a force perpendicular to its motion, all you do is you deflect the particle. You cannot speed it up or slow it down. Okay? So, using a magnetic field, you can only deflect a charged particle. You cannot add energy to it. You cannot do work on it. So you can't add or decrease its energy. Okay? All right, so the magnetic force on a moving charged particle is given by this cross product. The magnitude of the force is QVB times sine theta. There's the angle theta. Theta is this angle between the velocity vector and the magnetic field vector. Okay. So can the force ever be zero? If a charged particle is moving in a magnetic field, can the force ever be zero?
It would be moving, so there would always be some sort of direction to it.
Okay. For theta equal to 180 degrees, what is sine theta? 0. For theta equal to 0, what is sine theta? 0. So, when the particle is moving either parallel to the magnetic field or anti-parallel to the magnetic field, there won't be any force. So that's the only time when it doesn't exert a force. Okay? Okay, do you guys understand this? This law? Okay, again, now I'm going to show it to you with my hand. So use your right hand, point your fingers in the direction of the velocity vector, and then turn toward the magnetic field vector. And your thumb is pointing in the direction of the force. Okay? No, you got to use your right hand. Okay. So start off pointing in the direction of the velocity vector, turn toward the magnetic field, and your thumb points in the direction of the, okay? Sometimes you're not able to turn your hand in where the velocity vectors and the magnetic field vectors are pointing. So then you have to use the right hand screw rule. Okay. So here's the first vector, here's the velocity vector, here's the magnetic field vector. You turn a screw from velocity to magnetic field vector. If you turn a screw like this, which way will it move? That way. That's the direction of the force. Here's the velocity vector, here's the magnetic field vector. If you turn a screw like this, which way will the screw move? I'm sorry?
Down.
Up. if you're unscrewing this.
Oh.
Okay? So you want to remember that rule because there will be situations when you won't be able to turn your hands. Okay? Again, you're always turning from the first vector to the second vector, and the direction in which the screw moves, that's the direction of the force. Okay? And again, remember, so the velocity vector and the magnetic field vector form a plane, and the force is perpendicular to the plane. So you've got to figure out one of two directions. All right, now let's look at this equation. So this, for a positive charge, I told you that rule. What if the charge is negative?
Down.
It's in the opposite direction. Okay, so figure out, always remember the direction for the positive charge, and for a negative charge, the force is in the opposite direction. Okay, so let's say if this was a positive charge, there's the magnetic field, the force on this guy would be in that direction. If this was a negative charge, the force would be in the opposite direction. Okay? All right, so again, so here the velocity vector, there's the magnetic field vector. The force is perpendicular to the plane containing the velocity and the magnetic field. Okay? Again, this is a good rule, except that there will be situations when you won't be able to turn your hands appropriately. Okay, so then you want to use the right hand rule. So again, the right hand rule is you're turning from the first vector to the second vector. If you turn a screw like this, the screw would move in that direction, and that would be the direction of the A cross B. Okay? So the magnetic force exerted on a negative charge is in the opposite direction to that exerted on a positive charge. Okay? So the right-hand rule is for the positive charge. You could use your left hand for a negative charge, but yeah. Okay. So here's the force on a charged particle. Okay. So if you had a charged particle in the presence of an electric field, the force on the charged particle is in the same direction as the electric field, and it's perpendicular to the magnetic field. Okay, so electric fields can speed up particles. They can increase the energy of the particles since they're in the same direction as the force is in the same direction of the electric field. You can increase the energy of the particle. An electric field can increase the energy of the particle. The magnetic field cannot increase or decrease the energy of a particle. Okay? It can only deflect its motion. Since magnetic force is perpendicular to the direction of motion of a charged particle, it can do no work on the particle and hence cannot change its energy. Okay? All right, so we'll talk about the units of magnetic fields. Okay, so here's the force equation. Okay, the magnetic field is magnetic field again just is force divided by Q over V. Force has units of newtons. Q charge has units of coulombs. Velocity has units of meters per second. Okay. And we can combine coulombs per second into amperes, so Newton, ampere, meter. Okay, so magnetic field has units of Newton, ampere, meter. Okay. Now, whenever in physics you get a combination of units, you give it a new name. Okay, and this is called a Tesla, after Mr. Nikolai Tesla. Okay, that's after whom the car is named. Okay. So 1 Newton divided by 1 ampere, 1 meter is 1 Tesla. A Tesla is a large field. Okay, it's a very strong field. I don't know if you guys have had MRIs recently. Well, if anybody's had MRIs, but in an MRI machine, you can have up to 3 Tesla fields. The higher the field, the sharper the image. Okay, let me show you what happens, how strong the field is. This is an old MRI machine. This is probably about a half a Tesla, or at best 1 Tesla. And what, do you guys know what this picture is?
So you're not supposed to bring metal into an MRI?
So what happened was, this was a gurney that was brought in, and somebody turned on the machine. The gurney, I don't know if the patient was on there, but so that's how strong that magnetic field is.
Yeah, I've heard stories about people like
Mhm.
who like carry like guns
Mm-hmm.
and they don't listen to the warning. And the gun just
Oh, wow. Yeah.
takes to their
Yep.
place all the time.
So the fields are very strong. Okay. All right. So let's go back. Okay. So a Tesla is a strong field, but that's the unit of the field. I think this FSU has a National High Magnetic Field Lab, and they produce fields up to 100 Tesla. Okay.
How large was the field?
I'm sorry?
How large was the field,
What field?
the magnetic field?
Where?
If it was that strong, like how big was the field? From the-
Oh, volume of the field? I'm not sure. Yeah, maybe a foot cube. So a Tesla is a strong field. The Earth's magnetic field is 1/10,000th of a Tesla. So we define, if you want to measure fields of a planet, so if you wanted to measure the field of Earth's magnetic field on the surface of the Earth, a Gauss is a good unit. And a Gauss is 1/10,000th of a Tesla. Okay. But the SI unit for a magnetic field is a Tesla. All right. So here are some fields. Strong superconducting magnet. I mean, this is old info, but anyway, about 100 Tesla. MRI machines. The MRI machines that are used in doctor's office go from 0.5 to 3 Tesla. Okay. The stronger the magnetic field, the sharper the image, the better the resolution, and the more money it costs you. Okay. So depending on what it is that they're trying to diagnose, they'll send you, well, they'll tell you what kind of resolution you want. You go buy a magnet in a store, the kind you play with, that's 1/100th of a Tesla. Yeah. On the surface of the Earth, it's 10,000th of a Tesla. In your brain, because of the neurons firing, all the currents flowing, the fields are about a trillionth of a Tesla. Yeah. And this is interesting. Okay, so here's your brain, let's say. And let's say you hear something and this part of your brain fires. The magnetic field is strongest here, so they can use wires to detect the activity of your brains. Okay, so depending on, let's say you hear a joke and this part of your brain fires, and so this sensor goes off. Um, So So there are the sensors being used to detect brain activity. Yep. So here's a non-invasive procedure to detect brain activity. All right. All right, we'll stop here today. We'll see you guys in lab in a little bit.